Assalamualaikum warahmatullahi wabarakatuh and greetings all. Alright, so today I would like to introduce you with our new chapter, which is chapter 9 entitled Magnetic Force and Materials. In this chapter, we will cover firstly the magnetic force, secondly the magnetic material, and lastly induction and energy. In our previous topic, you has been introduced to magnetic field intensity and how to find the field by using whether the Biot-Savart law or Ampere's law. The analysis is depend on the type of current source, which is whether it is a filament current, the surface current, as well as volume current, and the condition of the current, whether it is a finite source or the infinite current source. In this chapter, we will see the effect of the magnetic field when the existing of magnetic material, because so far our analysis is done in a vacuum or free space. So for the first part, so we will discuss about the Logan equations relating to the magnetic force. The Logan equation said that the force on a moving charge can be defined as F equal to QU cross B, where the F equal to magnetic force, Q equal to total charge on currents, U is velocity of the moving charge, and B is magnetic flux density, where the force takes place. So that means, is there any conductor carrying current with a certain velocity with the existing of the magnetic field? So basically the conductor will experience the force, right? Let's see the current source. As we know, the current source J is equal to rho VU. J is defined as a current density. The current density is a charge density moving with velocity of U. And you already know the current element, which is a J dV, or we can expand into U rho V dV. And you know that the rho V dV is equal to U dq. So the conclusion is I dl is equal to Js ds equal to J dV equal to U dq. So we can replace dq U is equal to I dl in magnetic force equation. Therefore, the dF equal to dqu cross B equal to I dl cross B. So basically this is our final equations. The force equal to the integration of I dl cross B. For surface and volume current density, F equal to the surface integration of Js ds cross B, and also equal to the volume integration of J dV cross B, where the B is the external field where the force takes place. When you see from this case, if you have a loop carrying a current inside a magnetic field produced by other current source, so basically the loop L2 will experience the force F2. So the force F2 can be expressed as the integration of the I2 dL2 cross B12. If you can see from this expression that dL2 is basically a vector form, so it depends on the direction of the current. If the current in the positive direction, it will be positive. When the current in the opposite direction, it will be negative. Let's say example 1. Find a magnetic force per meter between two infinite filament conductors. The conductors are parallel to each other and the current flow are in opposite directions. Right, so you can see from the figure we have the first filament current, the I1, carrying I1 in the positive Z direction, and then we have the reverse current. So at the second conductor, I2 flowing in the opposite direction, and these two conductors is separated by distance d. Alright, because our analysis is on our second current, right? So the force is basically the F2. The F2 equal to I2 dl2 cross B12. So the B12 here is basically the field created by the first current source. By using the Ampere's law, so you have to refer to Ampere's law to find the magnetic field intensity for the filament currents. So the B1 is equal to mu naught H1 equal to mu naught phi I1 divided by 2 pi R. Alright, because we have the two filament, so each filament has their own phi. So we have to change the coordinate system into the mutual coordinate system that can be linked these two situations. Right, so basically we can change the phi into the negative x direction. But how? We can use this expression. The direction of phi is equal to the direction of current cross the direction of r. So for the first case, the direction of current in positive z direction and the r is in the positive y direction. So we have the phi equal to z cross y. So the z cross y is equal to negative x directions. How about the r? Okay, so basically the r is basically the distance between the two conductors, which is in the y direction. So we can change r into y. We can see from the figure that the current I2 is basically d meter away from the current I1. So we can change y into d. So the force dF2 equal to I2 dL2 cos B12. So to find the total force F2 is equal to the integration of I2 with a negative z dz. Okay, why we got negative z dz here? Because the direction of current I2 in the direction of negative z. Because our dl is a vector, so we put negative z dz. Cross negative x mu naught I1 divided by 2 pi y. This is will later on convert to d. Alright, so when you solve the cross product of the negative z and negative x, so you will get y. So we have a y mu naught I1 I2 divided by 2 pi 1 dz. So you have to integrate with the dz. So we can see there is no z here, so we can put outside. So integration of z from where? From 0 to L. Because our filament is very long, so we just put as a 0 to L. So this is our solution for F2. So the final solution is the force per length. So you have to bring the L to the left hand side. So the final solution is equal to, in the direction of y, mu naught I1 I2 divided by 2 pi d Newton per meter. So this is our answers. Okay, this is for your own revision related to Lorentz equations. Right, please study example in page 362 Sadiku related to long wire and rectangular loop carrying current. And the second example, please study example in page 263 Sadiku related to coaxial line carrying current, because I will not discuss this.